Welcome, everyone, to The Deep Dive, the show where we try to slice through complex research, dense articles, all that stuff you mean to read, really, to bring you the essential nuggets, the useful bits. We want to give you that shortcut to being genuinely well-informed, maybe with a bit of humor along the way. Today, we're tackling something, well, pretty common, actually, whether you're prepping for a big presentation, exploring a new field, or just, curious. How do you make sense of complex data, especially when you're trying to measure concepts that are kind of abstract, like in social sciences or business? I mean, really think about it. How do researchers even start measuring something like customer loyalty or brand perception or employee engagement? How do they do that accurately? Really capture what they mean. It often feels like trying to weigh smoke, doesn't it? Or grasp water. What sophisticated tools do they actually use to get a handle on these invisible forces?
It absolutely can feel like that, like trying to pin down something intangible. And that's really the core of our deep dive today. We're stepping into this fascinating world of how researchers go beyond just collecting data to actually measuring these abstract concepts with precision, and crucially, how they confirm their measurements are sound, valid, reliable. Our main guide for this journey is a really important paper by Joe Hare Jr., Matt C. Howard, and Christian Nitzl. It's titled Assessing Measurement Model Quality in PLS-SEM Using Confirmatory Composite Analysis. Quite a mouthful, but important stuff. So the paper's purpose, and really our mission for you, the listener, is to give you a clear understanding of this intricate process. Assessing measurement quality. We're going to focus particularly on Confirmatory Composite Analysis, CCA, which operates within this broader thing called Partial Least Squares Structural Equation Modeling, or PLS-SEM. By the end of this, you should hopefully grasp what CCA is, how it's different from other methods people might know, like Confirmatory Factor Analysis, CFA, and also understand why it's becoming such a vital tool, especially when the goal isn't just explaining what happened, but actually predicting what might happen next.
Prediction. That really is the holy grail for so many fields, isn't it? Moving beyond just description to actual foresight. But okay, before we get into the nuts and bolts of CCA, this whole idea of measurement quality, making sure you're measuring what you think you're measuring, that can't be a new problem, can it? Researchers must have been grappling with this for ages.
Oh, absolutely. And what's really fascinating, and the paper highlights this well, is how these, seemingly modern statistical techniques have roots stretching back over a century. They've evolved from these foundational ideas in psychometrics. The whole process of examining measurement quality, it's been a core challenge for decades. It really started in psychometrics. That's the science of measuring mental capabilities, processes, abstract stuff. Early on, this whole process was often just called item analysis. Think about the first attempts to make a reliable psychological test. Researchers would painstakingly use stats to select the right items, individual questions, basically for a test. They were striving for precision. J.P. Guilford, he's often credited with coining item analysis back in, I think, 1936. And the goal then, which is remarkably similar to today, was to refine this potentially huge pool of questions down to a smaller, precise set of indicators, efficiently measuring some specific concept. It was about finding the signal in the noise, really, distilling complexity.
So even way back then, they were wrestling with the same core issue: how to get to the heart of a concept with the fewest, most accurate questions. That's surprisingly relatable, even for designing a simple survey today.
Exactly. And this early work, it wasn't just a blip. It laid the groundwork for what we now call classical test theory. Charles Spearman, for instance, huge figure, way back in 1904. He was dealing with that inherent wobbliness you mentioned in measurement. He developed methods to correct for measurement error in correlations. He called it attenuation. Imagine trying to measure a room with a stretchy rubber band. Spearman was figuring out how to account for that stretchiness, estimate the true correlation if you could measure perfectly. He also developed reliability indices for this. And beyond Spearman, you had others, George Ewell, Fritz Cooter, Marion Richardson, Louis Gutmann. They all pushed classical test theory forward, continuously improving how we understand and quantify these tricky social phenomena. Now, classical test theory has been added to since then, of course. We have item response theory, generalizability theory, more sophisticated models, but its historical importance in shaping how we think about measurement quality is just immense. These pioneers really set the stage for everything we do now with advanced stats. It's a good reminder that even our modern tools have this deep history.
That's a great bit of context. Really shows how today's methods stand on the shoulders of giants. A century of refinement. Okay, so with that groundwork laid, let's jump forward a bit to something maybe more familiar to folks in business or social sciences today: Exploratory Factor Analysis, ESA. It's more structured cousin, Confirmatory Factor Analysis, CFA. Then we'll see how PLS, SEM, and CCA fit in. Let's kick things off with EFA. The paper says this was also initially proposed by Spearman back in 1904 again. I often think of EFA like you've got this massive, messy pile of puzzle pieces. No box top, no picture. You're just digging through them, trying to see what pictures naturally emerge. Does that capture how researchers use it?
That's actually a really good analogy, yeah. The EFA is precisely that. It's for data reduction, sure, but more importantly for discovering underlying structures in the data. Exploring theories. The statistical goal is to find a smaller set of these unobserved latent constructs, those hidden factors like trust or satisfaction or commitment from a whole bunch of individual items or variables. And the ultimate goal, after you explore, is to build reliable, valid scales based on what you find. The key word is exploratory. You use EFA when you start with no strong prior ideas about how the variables might clump together. You might have, say, 50 questions about company culture. EFA helps you see if they actually boil down to a few core dimensions, maybe innovation culture or collaboration culture. You let the data guide you.
So it's about seeing what patterns just emerge from the raw data. Sounds super useful, especially early on when you're first trying to get your head around a new concept or build a new scale.
Exactly. Now, within EFA, the paper mentions two main ways to do the calculations: principal axis analysis and principal components analysis, or PCA. Principal axis analysis, it mainly looks at the common variance shared among the indicators. That's the part of a variable's variability that it shares with all the others in the analysis. Unique variance and error are kind of set aside. PCA, though, it tries to explain as much of the total variance as possible. So it includes common, unique, and even some error variance, though the error part is usually seen as tiny after extraction. There's been this long-standing debate, about which is better, conceptually, practically. But a key point from the paper is that often in practice, the results you get from both PCA and principal axis analysis end up being very similar, especially if you have a lot of indicators, say, more than 30. Or if the communalities, that's how much of an item's variance is explained by the common factors, are pretty high, like over 0.6. So for many uses, the choice might not actually make a huge difference to the final structure you find.
Okay, that's good to know. Practically speaking, the difference might not be as massive as the debates suggest sometimes. So EFA is for exploring. What's the next step in this evolution? Confirmatory Factor Analysis, TFA, sounds like it goes beyond just exploring.
It absolutely does. CFA is a major leap forward. It really took off with covariance-based structural equation modeling, CB-SEM, which became big in the early 80s. The key difference is right in the name: confirmatory. Instead of discovering relationships, CFA is all about testing existing theories or specific hypotheses about how your variables relate to those underlying constructs.
Right. So if EFA is figuring out the puzzle picture from the pieces, CFA is when you have the box top, you've got the theory, the picture, and you're checking if your pieces, your data actually fit that picture, confirming your theory.
Spot on. You start with a clear theory-based hypothesis about which variables should load onto which constructs. The CFA process itself is really rigorous. It's a mix of qualitative thinking and statistical checks. You look closely at item reliability, construct reliability, different kinds of validity, like face validity. Do the items look like they measure the concept? Content validity, do they cover the whole concept? Then you get quantitative. Convergent validity, do items measuring the same thing correlate strongly? And discriminant validity, is your construct truly distinct from others, not just overlapping? And finally, CFA looks at the goodness of fit of the whole model. How well does your theoretical model match the actual data you collected? A key philosophical point. CFA constructs are based on common variance. They only focus on the shared variability among indicators that's due to that underlying factor. So, connecting this back to the bigger picture for researchers, CFA is about rigorously testing a theoretical relationship. It's providing empirical proof that your measurements capture the specific construct you think they do according to your theory. It's a hallmark of rigor.
Okay, so EFA explores, CFA confirms based on factors and common variance. But then around the same time CB-SEM and CFA were getting popular, Herman Wold developed PLS-SEM, partial least squares SM, in '82. Sounds like it came from a slightly different angle, maybe more flexible.
That's a great way to put it. PLS, often called variance-based SEM, was designed as an alternative. And yes, it offered significantly more flexibility than CB-SEM, but for a while its development didn't quite keep pace with CB-SEM, partly because there wasn't easy-to-use software readily available. When PLS-SEM really started gaining traction, maybe around 2005, especially with software like Smart PLS becoming available, well, researchers, maybe just for convenience or because it seems similar, started calling their measurement model confirmation CFA too, just like in CB-SEM, and that understandably led to quite a bit of confusion, and maybe some imprecision in the terminology. So to fix this, Ed Rigdon, a top methodologist, suggested in 2014 that PLS-SEM users should explicitly call their constructs composites, not factors. This was crucial because mathematically and philosophically they are different, and this distinction directly led Hensler and others in the same year to propose Confirmatory Composite Analysis, CCA, specifically as the right way to confirm measurement models in PLS-SEM. It was basically formalizing a necessary distinction.
Ah, okay. So CCA is like the PLS-SEM specific version of CFA, tailored to its unique way of doing things. It clarifies the different goals. The paper has that helpful Table 1 comparing EFA, CCA, and CFA. Can you walk us through some key differences from that table?
Sure. Table 1 really nails the core differences. Let's look at a few things. First, there's statistical objectives. EFA, primarily data reduction, exploring patterns, discovery. CCA and CFA both aim to confirm measurement theory, but CCA explicitly adds another goal: prediction of dependent variables. It's not just confirming measurement, but how well it predicts outcomes.
Prediction again. Okay, that's a clear difference.
Yeah. Second, their starting point. EFA ends by identifying factors. CCA and CFA start by proposing theoretical constructs you want to confirm. Third, how they handle variables. EFA often looks at independent variables separately in the factor stage. CFA looks at everything together as measurement models. CCA also analyzes them together, but its focus is simultaneously on measurement and prediction.
Okay. And you mentioned some more technical differences.
Right. A couple of subtle but important ones: rotation and correlation. EFA often uses orthogonal rotation, which creates independent, uncorrelated factors by design. CCA and CFA usually result in correlated constructs, which, let's face it, is often more realistic in social sciences where things are rarely totally separate. And finally, determinacy. Factor scores in CF and EFA are indeterminate. You can't perfectly calculate them from the observed variables. There's always some estimation. But composite scores in CCA are determinate. They can be precisely calculated. This is a big deal for researchers because you can then use these exact scores in later analyses, like for individual predictions, without that estimation ambiguity.
So what this really means for researchers is, well, it's about having the right tool for the job. And CCA seems like this specialized tool for PLS-SEM with some unique advantages. It sounds like CCA offers a broader view of measurement than just EFA, and it really expands confirmatory analysis beyond just traditional factors.
Precisely. It lets researchers leverage PLS-SEM's strengths for more kinds of questions. For instance, the paper notes CCA often lets you keep more items measuring a construct, which can improve content coverage, make the construct validity stronger. This is partly because CCA, using PLS-SEM, focuses on explaining total variance, not just common variance like CFA. That difference can lead to richer constructs, and as we'll get into, CCA is uniquely suited for formative measurement models. That's a huge advantage over traditional CFA.
All right. That sets the stage perfectly. Let's dive deep into CCA itself then. You said it's a systematic process for confirming measurement models in PLS-SEM. And critically, before you even start CCA, you have to make this fundamental choice. Is your measurement model reflective or formative? That sounds like a massive first step.
It's not just critical, it's foundational, absolutely paramount, and it must be based on measurement theory. If you get this wrong, the whole quality assessment goes sideways. This choice dictates how you conceptualize, specify, and ultimately check the quality of your measurements. Let's start with reflective measurement models. Here, the indicators, your survey questions, for example, are assumed to be influenced by or caused by the underlying latent variable. Think of them like symptoms of an illness. If someone has the flu, that's the latent construct the symptoms manifest. Fever, cough, fatigue. The flu causes the symptoms. They reflect the flu. In a PLS-SEM diagram, the arrows point away from the construct to the indicators, implying causality flowing outwards. The composite score is calculated from a linear combination of indicators using correlation weights. If the construct changes, theoretically, all its indicators should change too.
That makes intuitive sense. The underlying thing is real. The indicators are just its outward signs. But then formative measurement models seem to flip that completely. That sounds like a big conceptual jump.
They absolutely do. The logic is inverted. In formative models, the indicators are seen as causing or forming the construct. A change in one indicator can change the construct. But a change in the construct doesn't necessarily mean all indicators change together. The analogy I like is ingredients in a cake. Change an ingredient, add more sugar, use different flour, and you change the cake itself. But if the cake becomes more delicious, the construct changes. That doesn't mean the amount of sugar suddenly changes on its own. The ingredients form the cake. They define it. So for formative models in PLS-SEM, the arrows point from the indicators to the construct, reflecting that causal flow. And regression weights are used to calculate the score. This directionality is super important. And here's the absolute core insight, the real aha moment that can trip people up. Because the indicators define the formative construct. If you remove even one indicator or add a new one, the definition of that construct changes completely. It's not just a slightly different measure of the same thing, it's fundamentally a different concept. This is totally different from reflective models, where indicators are often somewhat interchangeable as they're all just reflecting the same underlying thing.
Wow, that's huge. So if I'm measuring something like, say, socioeconomic status using income, education, occupation, and I decide to drop occupation, I'm not just refining the measure, I'm actually measuring a different socioeconomic status. That completely changes how you approach design and what you can claim. It means you have to be incredibly precise about your definitions from the start.
Exactly. It forces much more deliberate, theoretically grounded thinking when defining formative constructs. Each indicator is part of the meaning. So once you've made that crucial reflective versus formative call, the paper lays out specific steps for assessing quality with CCA. Let's start with the reflective models first, following Table 2 in the paper. Right, there are 7 key steps for reflective models, each with important details and rules of thumb. First step, assess indicator loadings and significance. The loading shows the strength of the link between an indicator, like a survey question, and its construct. Guideline. Standardized loadings should ideally hit at least 0.708. Why that number? Because if you square it, you get 0.50, meaning at least half the indicator's variance is explained by the construct. You also need to check the t-statistic, usually needs to be above plus or minus 1.96 for significance at the 5% level. You get this via bootstrapping in PLS-SEM, or check confidence intervals, make sure they don't include 0. Step 2 builds right on that. Indicator reliability. This is simple. It's just how much variance is shared between an indicator and its construct. You just square the loading. Tells you how much signal from that one question comes from your concept. Step 3 moves up a level. Composite reliability, CR versus Cronbach's alpha. Both measure construct reliability, the internal consistency of the whole set of indicators for a construct. Rule of thumb for both. Above 0.70 is generally considered good, but, and here's a key nuance, composite reliability, CR, is usually preferred. Why? Because it's weighted. It considers that some indicators might contribute more strongly than others. It's more accurate than Cronbach's alpha, which assumes all items contribute equally.
So CR is smarter because it knows not all questions pull the same weight. Some are better reflections. Makes sense.
Precisely. And here's where it gets really interesting, a bit counterintuitive maybe, an aha moment. While higher reliability seems good, if your CR is too high, like 0.95 or more, that can actually signal a problem.
Too high. How can it be too high?
Yeah, it often suggests redundancy. Your items are measuring almost the exact same tiny thing. There's no diversity.
Our questions are too similar, like asking the same thing slightly differently. How does that affect the usefulness of the construct? It sounds like a paradox, too good is actually bad.
That's exactly the paradox. Excessive redundancy, while boosting reliability numbers, can narrow your construct's scope. You might be perfectly measuring a tiny sliver of customer loyalty, but missing other vital parts because your items are too alike. They don't capture the full breadth. It raises that question, are we overfitting? Just asking the same thing repeatedly instead of capturing the richness of the concept. It can inflate precision but hurt the construct's overall validity and usefulness. Step 4 then is average variance extracted, AVE. Another key metric. It measures the average variance shared between the construct and its indicators. You get it by averaging the squared loadings, the indicator reliabilities for the construct, the standard criterion. 0.50 or 50% or higher means on average at least half the variance in your indicators comes from the construct they're supposed to measure. Good convergent validity at the construct level. Step 5 is discriminant validity, and the go-to method here is the heterotrait monotrate ratio of correlations, or HTMT. Discriminant validity checks if your construct is distinct, empirically different from other constructs in your model. The core idea. Variance within a construct, what AVE tells us about, should be much greater than the variance share between that construct and any other construct. The paper gives clear cutoffs for HTMT, usually 0.85 or 0.90. Plus, you need significance testing using confidence intervals to ensure the HTMT value is significantly below 1. HTMT is generally preferred over older methods like the Fornell-Larker criterion because it's better at spotting problems, especially in complex models.
Okay, so we've checked how items group together, how reliable that grouping is, and how distinct it is from other concepts. But what about how it fits into the bigger theoretical picture? That sounds like nomological validity.
You got it. Step 6 is nomological validity. This is an extra but powerful check on construct validity. It involves correlating your construct's composite score with other concepts in the broader nomological network. That network is just the theoretical web of related concepts your study sits within. So if your model links job satisfaction and performance, you might also have data on organizational commitment or maybe job type. Full-time, part-time. Nomological validity means checking if the correlations between your satisfaction performance scores and these other things align with existing theory. Is the direction right? Is it significant? It shows validity isn't just internal consistency, but how the construct behaves in its theoretical neighborhood. Does it make sense with what we already know? And finally, for reflective models, step 7. Predictive validity. This assesses how well a construct predicts scores on some future criterion measure. The key here is future. It's about predicting something collected later in time. Unlike concurrent validity, where everything's measured at once. Example, measure employee engagement today, then measure actual retention 6 months later. Correlating those assesses predictive validity. It's about the construct's real-world punch, its ability to forecast outcomes, which is often the ultimate goal, right?
Absolutely. Real-world utility. Forecasting, that's the goal for so many. You also mentioned construct invariance and MICOM briefly, but said it's not always required. Why is that?
Right, it's more advanced, but crucial sometimes. Construct invariance, often checked with the MICOM procedure, becomes really important, often mandatory, for studies comparing groups, like across cultures or over time in longitudinal studies. Its purpose is to make sure your measurement works the same way across these groups or time points. So if you see score differences, you know it's a real difference in the construct, not just your measurement acting weirdly in one group or at one time point, making sure the ruler isn't bending, basically.
Gotcha. So those are the 7 steps for reflective models. But you said formative models are a different game entirely. Different rules, different logic. Why? And what are those rules?
Yeah, completely different ballgame. Because formative indicators form the construct. They don't necessarily correlate or move together. So those standard internal consistency measures like CR or AVE, they just don't apply. They're based on indicators reflecting a common cause, which immediately raises that question. If indicators aren't expected to move together, how do you assess quality? The whole approach has to shift. There are 5 key steps for assessing formative models. First is convergent validity, often checked using redundancy analysis, how it works. You check if the formative construct correlates highly with a separate reflective measure of the same construct. This reflective measure could be a single global item like, overall, how innovative is your team? If team innovation is your formative construct made of things like R&D budget and patent numbers. Or it could be a multi-item reflective scale. Guideline, minimum path coefficient of 0.70 between the formative construct and its reflective check. Practical point. You need to plan ahead and actually include that reflective measure in your study design.
Okay, so even though it's formative built from indicators, you still need that outside reflective check to ensure it's capturing the intended concept. Clever. What about multicollinearity? Sounds like a big worry here.
Spot on. Multicollinearity is a major concern. That's step 2. Indicator multicollinearity. High correlations are good for reflective indicators. They reflect the same thing. But high correlations between formative indicators, that's bad news. Why? Because formative models work like multiple regression. Indicators are like predictors forming the outcome, the construct. High multicollinearity messes up the weights, like beta coefficients, making individual contributions unreliable. We check this with VIF, variance inflation factor. Rule of thumb now, VIF of 3.0 or lower is best. Note that older advice said 5.0, but research now suggests that's too high. Also, if simple correlations between formative indicators are consistently over 0.50, that's a red flag. Solutions. Carefully remove indicators, but remember, that changes the construct's definition. Or, maybe better, create higher order constructs, grouping related indicators.
Right, changing the definition is a big deal. Okay, so multicollinearity is handled. Then you look at each indicator's unique contribution. How do you assess that if they don't necessarily cover?
Exactly. Step 3, size and significance of indicator weights. These weights are like beta coefficients in regression. They show the relative contribution of each formative indicator to the construct's score. Bigger weight, bigger contribution. Significance is checked via bootstrapping, usually aiming for PO 0.05, maybe 0.10 in small samples. A common issue, especially with many indicators, is low or non-significant weights. Suggests some aren't adding much. Again, creating higher order constructs is often the recommended fix if it makes theoretical sense. But making higher order constructs isn't always possible or right. So step 4 offers an alternative. Assess contribution of indicators using outer loadings. This looks at the absolute contribution, basically, the simple correlation between the indicator and the formative construct. Loading here is 0.5, and significant usually means it's important. But here's a huge nuance, a real aha moment. Unlike reflective models where weak items get dropped, for formative models, even if an indicator's loading is weak or non-significant, you might keep it.
Keep it, even if the stats look bad.
Yes, if it's theoretically justified. Maybe experts agree it's essential to the construct's definition. Removing it would change the meaning. So a formative indicator should never be dropped, only based on stats if theory strongly supports keeping it. This needs careful, qualitative judgment.
Wow, that's tough. Balancing stats and theory, a real blend of art and science. And the last step for formative.
Step 5, just like reflective models. Predictive validity. Does the formative construct, once built, actually predict scores on a future criterion measure? Reinforces its practical value.
Okay, that's incredibly thorough. CCA definitely provides a systematic way to validate these concepts, with tailored paths for reflective and formative. But once you've done all that hard work confirming the measurements, the real fun starts, right? Understanding the relationships between those concepts. So let's talk structural model assessment.
Absolutely, the next logical step. And let me stress this again. You must confirm your measurement models with CCA first, before touching the structural model. Trying to interpret relationships between constructs when the measures themselves are shaky. It's like building a house on sand. The whole thing is unstable. So structural model assessment also has steps laid out in Table 4. Step 1, evaluate structural model collinearity. Same idea as with formative indicators, but now between your independent constructs. High multicollinearity between constructs can distort the path coefficients the relationship strings. Again, VIF 3.0 is ideal. Bivariate correlations between constructs 0.50 might signal trouble. Solution: often creating higher-order constructs, combining related lower-order ones. Step 2, assuming collinearity is okay. Examine size and significance of path coefficients. This is where the rubber meets the road for your theory. Here's where you test your main hypotheses. Do the relationships you predicted actually show up in the data? Path coefficients are standardized, usually +1 to -1. Show strength and direction. Bootstrapping tells you if they're statistically significant. Closer to +1 or -1 means a stronger relationship, a bigger effect.
Right, where theory meets data, testing those core ideas. And the paper keeps coming back to prediction as a core strength of PLS-SEM and CCA. What are the key metrics for assessing that prediction power?
Yes, prediction is arguably PLS' biggest edge. There are several metrics, moving from in-sample prediction towards that gold standard, out-of-sample prediction. Step 3 is the R of endogenous variables. That's basic in-sample prediction. The classic coefficient of determination tells you how much variance in your dependent constructs is explained by the independent ones in your model. The big catch: it's in-sample. Only reflects predictive ability for the data used to build the model, can often overstate how well it predicts new data. That's overfitting. Researchers usually compare R values to similar studies in their field. Step 4 is the Fayette effect size, also in sample. This measures the specific predictive punch of each individual independent construct. You calculate it by taking a predictor out, seeing how much R drops in the dependent variable. Cohen's guidelines help interpret. 0.02 to 0.15 is small, 0.15 to 0.35 is medium, over 0.35 is a large effect. Shows the predictor's unique contribution. Step 5 is predictive relevance QR, also mainly in sample, but seen as maybe a slightly better hint of out-of-sample power than RO, often called blindfolding. Basically, QSIF-NUO means the model has meaningful predictive relevance for that construct. 0.25 is medium, 0.50 is large. It's a cross-validated check of how well the model reconstructs missing data points.
Okay, so RSFQQ, tell us how the model does on the data we have. But you mentioned the gold standard for real-world prediction. This is where it gets really interesting for anyone wanting predictions that actually work outside their data set. PLS predict.
Exactly. Step 6. PLS Predict. Developed by Shmueli and others in 2019, this is maybe the most crucial development for prediction in PLS-SEM. Why? Because those in-sample measures are Shmueli, FQ. They're known to overstate predictive ability for new data. The overfitting problem. Your model might look amazing on the training data, like a student memorizing answers for one test, but fail miserably on new questions. PLS Predict patches this head-on by assessing out-of-sample prediction. How it works, conceptually. It splits your sample into several equal groups, folds, say 10 folds, K10. It estimates your model using 9 folds, the training sample, then uses that model to predict the data in the one leftover fold, the holdout fold. Then it rotates. Each fold gets a turn being the holdout sample, predicted by a model built without its data. So every data point is predicted by a model trained on independent data, gives an unbiased look at predictive power.
That sounds really robust. Testing if the model learned to generalize, not just memorize. Any issues with sample size for those holdout groups?
Yes, definitely. The holdout samples need to be big enough. If your total sample is small, say N100, and you use 10 folds, each holdout is only N10. That's too small for stable predictions. Shmuley et al. Recommend a minimum holdout size of N30 for reliable results. Maybe N20 is okay sometimes, but below 30, you need to be cautious interpreting PLS predict results. To interpret PLS predict, you look at prediction errors like mean absolute error, MAE, or root mean squared error, RMSE. RMSE is usually preferred as it penalizes bigger errors more. The really critical part is comparing your model's RMSE or MAE against a naive linear regression model LM benchmark. This is a simple baseline prediction for each indicator.
Right, it asks that key question. How confident are you that your model predicts better than just a basic guess outside your data? PLS Predict gives that insight.
Exactly. Prove your model's worth. The interpretation guidelines are pretty clear. If your model has higher errors than the LM benchmark for all indicators, model lacks predictive power, not beating the baseline. Majority have higher errors equal low predictive power. Equal or minority have higher errors equal medium predictive power. Okay, but could be better. None have higher errors equals high predictive power. Ideal. Your complex model is genuinely better at predicting new data than a simple regression. Powerful validation.
That's incredibly valuable. Shifts the focus from just explaining variance to proving real-world predictability. That alone could change how people build models. The paper also mentions robustness checks as an advanced step. What's that about?
Right. Step 7, a broad but vital category. Robustness checks. This means doing extra analyses to stress test your model. Things like mediation, moderation, multi-group analysis, invariance testing, checking for nonlinear effects, or endogeneity issues. These are crucial. They're like sensitivity analyses. You see how your results hold up if you change analysis decisions or assumptions. It builds confidence that your findings aren't just quirks of one specific analysis, but are robust. Builds trust in your conclusions.
Okay, this deep dive has given us a really clear roadmap for assessment in PLS-SEM. Covered a lot, from history to cutting-edge prediction.
We certainly have. The core takeaway, hopefully. CCA and CFA are both valid, powerful ways to assess multi-item constructs. But, and this is critical, researchers must understand their differences theoretical, statistical, and use the right one for their specific goals, data, and how they conceptualize their constructs. Comparing CCA to CFA, CCA has clear benefits. 1, it often retains more items per construct. This can improve content coverage and validity, partly because it focuses on total variance, not just common variance. 2, it gives determinant scores, precise scores you can use directly in later analyses. 3, a big one, CCA works rigorously for formative models. That's hard, sometimes impossible with traditional CFA. And maybe most importantly, as we've stressed, when prediction is the main goal, wanting to know what will happen CCA within PLS-SE is clearly the preferred approach.
So it's not about one being universally better. It's about picking the right tool for your job, your question, your data. And those traditional goodness of fit stats from CFA sounds like they aren't the focus in CCA PLS-SEM. That's a big shift.
That's a huge point. The paper is explicit. Those traditional global fit indices, common in CFA CB-SEM, are generally not required for CA PLS-SEM. The focus shifts squarely to predictive validity, especially that robust, out-of-sample prediction via tools like PLS Predict. It reorients evaluation from how well does the model fit this data to how well does it predict new data, often a more practical, tougher test of real-world value. Which brings us to that strategic choice, when to use PLS-SEM in CCA versus CB-SEM in CFA. The paper offers guidelines. First, it hinges on your preference. Modeling constructs as composites, PLS-SEM, or factors, CB-SEM. Second, PLS-SEM is often better for theory development or exploration, while CB-SEM is classic for theory confirmation, unless prediction is the main goal.
So even confirming theory, if prediction is paramount, PLS-SEM might have the edge. What other practical things influence the choice?
Practicalities are key. Third, PLS-SEM gives more accurate estimates with smaller sample sizes, a big plus when large data sets are hard to get. Fourth, it's more likely to converge with complex models, many variables, many constructs. Fifth, as we've hammered home, if prediction is the priority, PLS-SEM is superior, especially with PLS Predict. CB-SEM just isn't built for that level of prediction focus. Sixth, if you absolutely need traditional global model fit stats, then CB-SEM is the way. However, it's important to realize PLS-SEM has evolved. It can now handle many advanced analyses previously seen as CB-SEM territory, endogeneity, invariance, mediation, moderation. Gives researchers enormous flexibility now.
That's really liberating for researchers. More tools, more flexibility. So the choice isn't which is better overall, but aligning method with research questions, goals, data, having all the tools and knowing when to use which.
Exactly. This deep dive into CCA really highlights that robust insights aren't just about what you measure, but how you measure it. And crucially, how well those measures let you predict future outcomes. It makes you wonder, what other established methods might be due for a fresh look, viewed through this powerful lens of prediction?
And for you, our listener, think about how understanding these nuances, these subtle but key differences in measurement, might change how you interpret research you see every day. Or maybe how you approach your own questions, especially when trying to figure out what's really going to happen next. That's all for this deep dive. We hope you feel a bit more informed, maybe a bit more empowered by this look into the heart of measurement.